talk to us about some of the most interesting questions in your field that is driving science.
Uh, yes, so I'm in elementary particle theory in the physics department. So I'm coming from a rather different perspective than some of the other panelists. And I'm going to simplify a bit 5 areas which are really high inquiry areas in my field. And here's one, the first one. If you put your hand out, you ask yourself how many atoms are in your hand, and it's something like, I don't know, 10 to the 30 or something, Avogadro's number times volume. Within each hand size, there's approximately 1 dark matter particle on the prevailing idea of dark matter. Just 1 out of 10 to the 30 or something. That 1 dark matter particle is absolutely critical for how our galaxy is rotating, how the expansion of the universe is operating. There's firm evidence that dark matter of some kind exists. We don't know what it is. It's a huge mystery. It is dominant, one of the dominant questions in physics departments. The second is, imagine you're at the early universe and there's a big explosion, and you know how things develop in a big explosion. You make a particle and an antiparticle. That's what big explosions do. Fundamental energy before you have matter. You make both in equal numbers. Well, in this room, you're all matter. There's no antimatter. If this table were antimatter and I hit my hand on it, it would be the most powerful explosion in the history of this galaxy. Okay? There's no antimatter out there that we know of. Why did that happen? Huge mystery. We don't understand. We have many ideas. There's experimental inquiries for it, but we don't know. Another, at any given moment, I will be Carl Sagan for a moment. There are billions and billions of neutrinos passing through you at every second. Those neutrinos are very elusive particles, very hard to study. You need detectors the size of Michigan Stadium filled with water to see Cherenkov radiation, to see one interaction per macroscopic time unit. Okay, that's how weakly interacting it is. It was discovered not long ago that they have mass. And if we had a panel here 50 years ago of particle physicists and other physicists, they would have sworn by their entire paychecks and their life savings that neutrinos were massless. How did they get mass? Don't know. We don't know how they got mass. We're still working on it. So one of the premier projects in particle physics in the United States is to figure out that, help figure out that question. Okay. 2 others very quickly. One is quantum mechanics at very high energies attached to gravity. How do they meld together? We don't fully know. We have really good candidate ideas and these string theory approaches. They lead to, if you follow the path for a few decades, they lead to problems that are similar to protein folding problems. 10 to the 500 minima. Where are we at in this minima? How do we decide how we got into our minima? How our present universe looks like? We don't know. We're investigating that problem. Last one. Higgs boson was discovered only 10 years ago. 10 years ago, in one day, there were articles on the web saying that the Higgs boson does not exist. So experiment was absolutely critical to establish that the Higgs boson was there. The Higgs boson gives mass to all elementary particles. Well, where did that mass come from? Why did the Higgs boson exist? And in particular, why is its mass so extraordinarily light compared to a characteristic scale of black hole creation? If you follow through basic quantum field theory arguments, which is the most basic fundamental description of nature is quantum field theory, it tells you it shouldn't be that light. It gives you really strong reasons to think it shouldn't be light. Why is it light? Huge issue. We're trying to figure that out.
Wonderful. That's 5 homework questions for you. Due on Monday. All right. That's really good. But now we'll go this way, and I'll ask you the hard question. How is AI, or how can AI help answer the questions potentially?
So in my area, in my expertise, I really love collider physics on answering many of those questions. Many of those questions that I described have a high energy collider experimental approach for determining the answer, trying to determine the answer. And high energy experimentalists, both in the US, at CERN, other places in China, have been on the forefront of utilizing machine learning and AI techniques to take extraordinarily complex data. The data is, if you could write it all to tape, at CERN alone, it's 1 petabyte per second. The detectors are bigger than the size of this auditorium. You cannot write all of that to tape, so you need extraordinarily fast electronics. The extraordinarily fast electronics to decide what to put on tape is fed through a machine learning system to, it's basically a classification problem. What is worthwhile versus not? So that's step 1 of AI. Step 2 is you form a cajillion little flickers in your detector all throughout a volume the size of this auditorium. In the old days, what you had to do is say, I think those cluster of flickers are an electron, and I think those cluster of flickers are a quark, and then you get some rough estimate of what's going on. Today, you can train these complex detectors on simulated data and on real data through bootstrapping mechanisms to not even worry about the ontology of the structures, but just what are all the things that flashed, and how does that connect to the theory? And that has been the most recent revolution in how AI is increasing accuracy and increasing the power of discovery in these different areas that I talked about earlier.
Yeah, thank you. That's very concrete.